So we talked in the last video about autoregressive models and telling how much we need to smooth. So let's talk a little bit more about smoothing. In modeling time series, we can use smoothing methods. This is the very basic forms. The two basic forms we look at: smoothing and regression-based models. Here we try to smooth out the irregular components so that underlying pattern will be easier to see. And regression-based models use multiple regression to estimate each component's contribution to the time series. Both that step of autoregression kind of helps us determine which ones we want to do. So there are two basic smoothing methods. One is moving averages. You can find this on page 178 in your course pack. And then there's exponential smoothing on page 179 in your course pack. The smoothing average, the weighting average, you just average the previous L-1 preceding measurements along with the current one. So that would be a moving average of length L. Or you could center it where you take the current value and put an equal number of preceding and successive terms. This kind of does a better job maybe perhaps of following the curve a little bit better, but it's a little more difficult to predict since we don't have the previous like L-1 or L2 data points to average. Another one is exponential smoothing, where you use a weighted average. And kind of the idea is that you weight the nearby observations more weight than farther away. You can actually center this weighted average and use different alpha for how much you want to weight nearby observations. The interesting thing about Minitabs is that can help you find out what the alpha might be for how much you should weight. The exponential smoothing is also interesting because of the mathematical way you do it. You're actually averaging all of the previous components when you get to a certain point. So let's take a look at clothing sales. Here I took a moving average of length 12 over the entire year, and you could kind of see how my sales are going up slowly. But by taking a moving average of length 12, I'm averaging the entire year to kind of take into account the seasonal fluctuations. Now, to determine how well the average works, we have to kind of talk about the forecast error. This is very similar to our residual error, and it's pretty much the same thing. It's what our observed value is minus what our forecasted value is, what our predicted value is in regression terms. So how closely does the model? And so there are common measurements for time series. One is just our good old friend mean square error, where you sum the squares of the residuals, but then you just average them. So that's our mean square error. And what that does, it penalizes large forecast errors with its squaring. The mean absolute deviation, or the MAD, just takes the absolute value and averages them up. The nice thing about the MAD is that it keeps the same units. And then the MAPE, the mean absolute percentage error, you take the forecast error and then divide by how much that is, and you average that out after you sum them all up and multiply by 100, and that gives you a percentage. And it gives you a percentage of this. So those are the common measurements. So if you look over here, you have MAPE, MAD, and MSD, which we're not going to talk so much about that one. But here you could see you get a 13 and a 12 point, or 1,224 for the mean absolute deviations. I'm sorry, it should be a 12.24 for that. So these are just kind of measurements you can do to determine how well it's working. And so if we go back to our data, this is for functions. If I go to my Federal Reserve graph, for my Dow Jones Industrial Average, here I've completed the lags and the fits, and like I said, I can go ahead and take a moving average of my Dow Jones Industrial Average or an exponential. Let's just do an exponential one here. So I'm going to go to Stat Time Series and do a single exponential smoothing on the Dow Jones Industrial Average. Here I'm going to put in a value, and I'm going to try to predict a number forecast from time, let's say 25. Let's try 3 for 25 and see what I get. See if it does. And here you can see the red, and the green Well, you can't quite see that as well, but it kind of gives me a forecast of what that'll be and kind of gives me an error here. So 23,225, I guess I didn't quite set it up right for the correct quarter. I had more quarters than I expected. I should have, I guess I had, oh my, 100, 200, 252 quarters. And so those would be my forecasts and can help me kind of predict. Let me try another one. I'm going to do the stat time series single exponential smoothing. I'm going to use the optimal one, and I'm going to generate a forecast from 250 and see what happens. So it's going to tell me, compute what my exponential smoothing should be. It gives me an alpha of 0.907, so it forecast most of it on the previous ones and gives me a little bit of the forecast here, about 28,642 for the next few times. So you can see there are a lot of ways to use time series for prediction. Let me try one more topic while I'm here and talk a little bit about non-stationary. I'm just going to go through this very quickly. Non-stationary possible features: if you see a trend or variance over time, varying autocorrelation structure over time, or period fluctuation, or an ACF which decays very slowly. That it gets below those red lines many times. So here's something that decays very slowly. You got like 6 or 7 blue lines outside of it. This is the serial sales. It also seems to have a trend, so this would not be so good. Here you have a Home Depot. Here I have a model for this. I could do a moving average of length 4, but you notice it's a little bit low, and I could do a forecast based on that. Let me go ahead and do that in Minitab. First of all, I'll need to make sure that I get my Home Depot sales. Here it is for do a time series plot for the Home Depot sales. And here you could see this. And I could do a moving average of, I think I wanted to do length 4. And I'm going to do a generate a forecast starting from the origin of 40. And I can either center it or not. I could probably only do one for 40. So if I do that, it gives me what my forecast will be of $18.27 billion in sales. So that might be a million of sales. I forgot whether it's millions or billions. And so the forecast, I guess it's in billion, 18.3 billion. But then I could do it for an exponential smoothing time. And there it forecasts me for 17.6. Notice this is a little bit lower, but it kind of depends. It's kind of a good compromise between a simple moving average and a seasonal component. A series with a strong trend such as this one will cause exponential smoothing to lag behind the data because there will always be a big jump. And a strong trend as it's going up, it'll always fall behind. And then you could do an autoregressive with lag 4. Here we fit the model with 4 lags, and then we could put it into our regression equation. I just went ahead and did an old regression, and I get 17.1. And we should really include the corresponding lag. And since we're going to head with quarters and the annual similarities, it would be, I did a lag of 4. And it would not have been a good idea to do an AR3 with model, since this precludes the seasonality. Let's go one more thing with the sales. What I might want to do is include the number of quarters that I've had since then. So I'm going to do add another quarter number here. Oh, I already used that in 1. So Q time maybe. And what I'm going to do is I'm going to put in pattern data, a simple set of numbers. I'm going to put it into Q time. Don't bother me. And I'm going to do a first value to 250 in steps of 1. And so that should get me down to the bottom. Nope, because I'm only in I'm not doing Home Depot. I'm not doing the Dow Jones Industrial Average. Let me delete these columns and try it again. I only had 40. So again, I'm going to make a column of make a pattern data here of a simple set of numbers. I'm going to do it for Q time. I'm going to start at 1, but I'm only going to go to 40 in steps of 1. And so now I can include a regression line from this. I'm going to fit the regression line to sales. And I'm going to include Q time and lag 1 to lag 4. And what this allows me to do, it kind of tells me, well, it's kind of going up by 275 million each quarter, but then I have to take in the various lags. My lag 2 is actually a negative number. And so if I wanted to plug in a value, I could do that. Let me see if I could do it off the fly here. Do a prediction. Let's do it at time 41. Actually, let me see if I can just put columns. Well, let me just put in my own. Let's do 41 with a lag of, I can't even, let's go move this down until I'm at 40. So I'm doing regression model, predict. I'm going to do the Q time at 41. And it's not liking me. So I thought this was data. It should be a number. Yeah. Sorry for this little delay, but 41, there we go. A lag of 18.772, a lag of 19.96, a lag of 17.550, and a lag of 15.125. And then I could get my prediction here that my fit would be $17.18 billion. Okay, so it's a little bit longer than perspective, but I hope that through this process, you have seen, just gotten a little taste of the power of time series and how you might just kind of use this for forecasting in the future.